everybody's having a good morning. We will continue with compositions of functions in just a moment. Just a few reminders. Remember, we only have a couple of days left. Friday is the end of the 6 weeks. I'm going to be submitting grades on that day. So Thursday, the day before, by 8:05 a.m., if you have any of the remaining retakes that you wish to go ahead and do, that includes the rational inequality exit ticket from last week and the second exam from last week as well. If you need those, come on in. Let me help you out. Friday, we should be well into inverses by then. We'll pretty much finish up compositions by today. Have a few problems left tomorrow, but on Friday, we're going to have an exit ticket over the difference quotient. I'm probably going to give you 15 minutes like I did last week on the rational inequality. That'll carry over into the next 6 weeks, be our first grade. I'm looking for Tuesday of next week to have a quiz over this material. So I'll go ahead and give you the assignment tomorrow, and that'll be due Monday. And then, we will just continue with the second 6 weeks. We should be able to start trigonometry pretty quick. Any questions? All right, well, let's get to it. Now, every class was a little different. How far did we make it with these problems? Did we get these 3 done yesterday? So we did finish the top 3. Okay. So we started talking about compositions of functions, which is what you see down here. Using the parentheses. And essentially what we're doing is evaluating one function inside of another. One thing that I kept saying quite often was the output, the answer to the inside function, must be in the domain of the outside function. You work your way from the inside out. And there were different ways to show this, like the notation. This is pretty common with the parentheses, but you could also use that little circle. Okay, so f composed with g of -2. We looked at it using tables, we looked at it with graphs, and currently we're on the functions themselves. Okay, so let's take a look at these 3 tasks, because I want you to see something. If function f is the quadratic 2x squared minus 3x plus 2, and g of x equals 2x plus 1, find f of g of -2. So today we're going to start to see the notation change. If you're given composition with a numerical value, then your answer is going to be a value itself. Okay, so f of g of -2. How will I actually simplify this? What do I do? There you go. G is the inside function. So I'm going to take that value of -2 and plug it in for every x that g has. So g of -2, that would be 2x, 2 times -2, plus 1, and that'll give me a what? -3. And this is what I was referring to. See, as far as the function goes, there is a relationship between x and y. For this input, -2, we got an output, an answer of -3, but I'm going to take this output and I'm now going to plug it into every x that the outside function f has. Okay. So now this becomes f of -3 instead of f of g of -2, because I already know g of -2. All right, so let's see here. 2x squared, 2 times -3 squared, minus 3x, minus 3 times -3, and then plus 2. All right, so what is a 2 times -3 squared? That is 18 plus 9, and then we have the plus 2, so it looks like we get 29. So the value of that composition, we ended up with 29. Okay, so any questions on how I did that? All right, now we want to remember that number because steps 2 and 3 are going to have something that makes this number pop up again. So let's see, task 2. Okay, given the same 2 functions, f and g, find an equation for f of g of x. So you'll notice for the composition here, you're not provided a numerical value. It just says f of g of x. Now, it does say find an equation, but I could easily say on a quiz or something, just write find f of g of x. Okay, so if you're not given a numerical value, then your answer is an equation. Okay, we want an equation, a brand new one that's going to represent the composition. So how would I actually do this? Does anybody have an idea? Hey, what do you think, sir?
You flip 2x plus 1 to every x.
That's exactly right. Instead of plugging in a value like we've been doing and working through the 2 functions, I'm going to take the function itself, That's my inside function. And I'm going to replace every x that f has. Okay, I'm going to insert one function directly into the other. Okay, so f of g of x, well, that's just f of 2x plus 1, because that's my input in this case, the actual equation. So that would be 2x squared, so that would be 2 times 2x plus 1 squared. Then we have a minus 3x, minus 3 times 2x plus 1, and we'll finish up with that plus 2. Okay. Now, we definitely don't want to go ahead and stop there. We want to expand, combine my like terms, just simplify it as much as possible. Okay, so let's start with the binomial. Somebody help me out. What do I get if I expand 2x plus 1? It would be 4x squared plus 4x plus 1. There we go. Now, what I've seen a lot of people do, they'll go ahead and write them out side by side. 2x plus 1 times 2x plus 1 in FOIL. That's great, okay, if it feels comfortable for you. There's another little shortcut method that I was taught. Again, it's silly, but it does work. It's a little rhyme that says you square the left, square the right, you double the middle, your answer's in sight. Okay, so let me kind of explain what that means. Think of your first term as the left term. The second term is your right. So square the left. If I square 2x, I get 4x squared. If I square the right, 1 squared is 1. Double the middle. It means multiply the two terms together. So 2x times 1, and then double that. Okay, and then it always gives you your trinomial. Okay, it's another one of those ideas. If you like it, great. If you don't need it, then don't worry about it. Okay, as long as you're able to expand the trinomial. But now I need to do what? Distribute the two. Okay, so somebody tell me what that would be. Okay, so now 8x squared plus 8x plus 2. Okay, and now we'll distribute across that binomial. Looks like a minus 6x minus 3, and then we'll have our plus 2. All right, and now it is just a matter of combining your like terms. So we only have the 1x squared, so 8x squared. What? Plus 2x, 8x minus 6x. And what? Plus 1. There we go. And a lot of times, this brand new equation that you just came up with, which represents the composition, we like to go ahead and name it something new. And it really doesn't matter what letter you choose. We already used F and G. Let's just go ahead and say we're going to call this H of X. Okay? It's a brand new equation. All right, but is everybody okay how I got that? Questions? Okay, well, step 3, it says, okay, use your equation that we just found for the composition to find f of g of negative 2. And this is where we tie it together. I just want you to see that, make this one connection. What did we get for f of g of negative 2? We got 29, right? So the idea is if I take the same input for that composition, if I were to plug it into this function, the one that represents the composition, well, what should happen? I should be getting the exact same answer. Okay, so this new function that we're calling h, let's plug the negative 2 in there. H of negative 2 equals 8x squared, so 8 times negative 2 squared, plus 2x, plus 2 times negative 2, plus 1. So 8 times negative 2 squared. 32. Looks like we have a minus 4 and then plus 1, which does give me what? 29. Okay. So sometimes you may be asked to find an equation representing the composition. Okay, but whether you evaluate an input using the composition or the new equation, the outcome should still be the same. Okay. Any questions? Easy, right? Okay, now this lesson here is pretty much just focusing on the skills related to our composition of functions. I wanted to go ahead and at least give you one example, okay, of how this could appear in the real world, because composition of functions are used. So I just put this one together after school. You don't have this, you can just kind of follow along if you want to. But it says if you drop a pebble into a pond, a circular ripple extends out from the drop point. Okay, the radius of the circular ripple is a function of time. Okay, but that makes sense. The radius depends on the time. The more time that passes, the larger the radius, meaning the larger the circle. The area enclosed by that circular ripple is a function of the radius. Okay, so in turn, the area depends on the radius. So area is a function of time through this chain of functions. Okay, while the area depends on the radius depends on the what? The time. So these together, area is a composite function of time. All right. And I'm just going to go ahead and elaborate a little further. Suppose that the radius of the ripple is increasing at a constant rate of 8 inches per second. R of t is going to be the number of inches of the radius as a function of t seconds after you drop that pebble in. Then what would the function R of t equal? 8x. Okay, so 8t. And if you want to change it to x, that's perfectly fine. Remember, the variable itself doesn't matter. Okay. So the radius function is 8t. 8 inches per second times however many seconds have passed. Now, recall that the area of a circle is pi r squared, where the radius is r. Okay, so you can write this notation. Now, what we were just doing a moment ago, where we took the equation for the inside function, okay, we plug it into the outside function, that's exactly what I'm going to do here. Instead of pi r squared, I'm going to replace r with this radius function. I'm going to go ahead and plug in 8t. Just like we were doing a moment ago. So what do I get if I square 8t? 64t squared. So I would go ahead and say that my area function is 64 pi t squared. Okay. See, I now have a function where the area depends on the time. The area is a composite function of time. Okay. So this symbol here is pronounced a of r of t. I mentioned it today, function r is what we call the inside function. Okay, because you apply the rule that defines function r first to t. Function a is called the, if we have our inside, we have our outside function. Okay, now this symbol right here, in fact, I wrote it just a moment ago. Instead of using all the parentheses, you could write it using what? That little circle. And this is by no means, remember, every way that they'll show up, but they're the most commonly used notations for our compositions. Okay. All right, so I just kind of wanted to give you an idea, just a quick example of how this can actually work out in the real world. And what's even better, the next time you and a friend are walking along a lake, or you're even walking by a puddle and someone throws a rock in, you could explain how that's mathematics in the real world and be even more cool. Definitely. Definitely. Because I'm sure it's one thing teenagers like is when one teenager just starts talking about math randomly.
Yeah.
Okay. See, I knew I was still with it. Okay. All right. Moving on. So let's go ahead and continue this idea here of finding a composite equation. All right, so I've got the same four from yesterday. F is a quadratic, G and H are both linear, and P is a rational. Okay, so I'm going to choose a couple of these that I would like to do, and then if you want to do some extras, we can, just like yesterday. We'll only go ahead and do every one of these if we want to. So I want to start with A. Find an equation for G of H of X. Okay, what's my inside function? H. So to find that equation, I'm going to take H, this linear, and I'm going to substitute it for every X that G has. All right, so G of H of X, this is actually G of 3/2 X minus 2. That's my input this time, the actual equation. All right. So G of X is 1 minus 2X, so this is 1 minus 2 times that equation, 3/2 X minus 2. So this one's going to be a lot easier to simplify than the previous one because we don't have to expand the square and all that. All right, so somebody help me. What do I get if I distribute a negative 2 through here? I would get 1 minus what? Minus 3x plus 4. So it looks like my equation is just going to be a negative 3x plus 5. There we go. So again, it's a new idea, but it just relies on your algebra skills. Okay, just expanding, distributing, like terms, all that good stuff. Okay. Now I would like to go ahead and try C because it's very similar to the one we just did a moment ago. Find an equation for f of g of x. F of g of x. So am I plugging equation f into g or g into f? G into f. G is the inside function. So every x in function f is going to become this 1 minus 2x. Okay, so f of gx, f of 1 minus 2x equals, so negative x squared, negative 1 minus 2x squared. What do we got here? Plus 3x, plus 3 times 1 minus 2x, and then minus 5. Okay. All right, now what I need is for somebody to come on up here and walk me through this problem. To go ahead and expand, distribute, all that good stuff. Now, who is somebody who has not been up to the board yet? Okay. Okay, well, Philip is pointing at Kashal. Okay. Well, we know who our friends are. Okay. Kashal, would you like to come up? But it's a good thing to come up on one of these where it's just algebra rather than, it's a much harder problem later on. There we go. He's standing up. All right. So Kashal is going to help me out with this one. Perfect, perfect, perfect.
So instead of doing this, I think it's easier to just negative 2x plus 1.
Okay, so he's going to flip around the binomial. In fact, I should ask, do you want the headphones? No?
Okay.
You sure? Okay.
And then you could just square that pretty easily by just 4x squared. And then you just multiply them and double it, minus 4x. Then you square the last term, and then you distribute this 3 minus 6x, and then you just bring down the 5.
Okay.
And then you could just simplify this.
Oh, there's just one detail. There you go. You got the square, but what's out in front of that group? So that's a negative.
Now I'll turn that into a positive.
That's a plus. And that's a minus. Okay, there we go.
So then you could simplify that.
So negative 4x squared.
Minus 2x. And then this would get you plus 2 and minus 3.
Okay. What do you guys think? All right, looks fantastic. Okay, negative 4x squared minus 2x minus 3. All right, that's it. That's all there is to it. Okay, finding the composition equation. Okay, now I'll leave it up to you. Would we like to take a look at either B or D? You want to look at D? Okay. Let's see. Now this one says find an equation for P of G of X. Okay, so what I'm going to do is plug function G. Okay, let me erase this right here. Into function P. So P of 1 minus 2x. So I'm plugging into a rational function. Up top, we got x plus 2, which would be 1 minus 2x plus 2 over x minus 3, which would be 1 minus 2x minus 3. Okay, and then we just go ahead and simplify here. What do I have up top? Negative 2x plus 3 divided by negative 2x minus 2. Okay. Now, in a case like this, you always want to see, because it's division, is there any way to simplify? I mean, the denominator can factor, but nothing's going to actually cancel out. I mean, if we really wanted to, I could go ahead and factor out the negatives and have those cancel, but I would say there's just no simplifying that I absolutely have to do. Would anybody like me to do it? Okay. So in this case here, yeah, we didn't have a whole lot of simplifying. So we're good. Okay, yes?
So is it just the discontinuity for the composite function, or does it keep the discontinuity from like the inside?
Actually, that's something we're going to go ahead and talk about. At the very end, I've got some problems coming up here because the domain here is going to be restricted. Okay, it's definitely going to be affected by the inside function that you input there. Okay. Yep, that's the last thing we have coming up. Yes. Okay. All right. Did anybody want to do B? Okay. Then before we go ahead and move on to the next section, we got to see a couple of rules that apply to these. Now, these aren't compositions per se, but what you're doing is applying an exact operation to the functions themselves. Okay, the four that we have: sum, difference, product, and quotient. All right, so I'll go ahead, give you a few seconds because you probably want to have that jotted down someplace. Wherever you feel you can fit it in. Okay, so the idea here is that we're not taking one function and we're going to substitute it into another as we've been doing for the composition. We're just going to apply the operation we're given directly to the equations. Okay, we're either going to add, subtract, multiply, or divide. And I've got just one quick example here before we go ahead and move on with the examples in your packet. So I just gave two linear functions, just made them up. F equals 2x minus 3, g is equal to x plus 7. And let's see here. Noe, what operation do you like? Adding, subtracting, multiplying, or dividing? Multiply. Okay. So let's say given these two functions, I had the expression f times g of x. Okay. Well, all I want to do is exactly what it asks me to. I'm going to take the function f, which is 2x minus 3, and multiply it by function g, which is x plus 7. Okay, and then I'm just going to come up with my equation. So let's see here. First, what would that be? 2x squared outside plus 14x inside minus 3x, and then last, minus 21. Okay, remember, FOIL is just a way to describe the distributive property. That's all it is. So it looks like we end up with 2x squared plus what? 11x minus 21. Okay. And the same operations apply. If I had f plus g, then I would simply take 2x minus 3 plus x plus 7. Okay, and get my new equation that way. All right, so what do we have on your paper? Okay, E. Find an equation for negative 6x times h of x minus f of x. Okay, so again, we're not plugging one equation into another. It's not a composition. We're just using the equations themselves. So the first thing here, negative 6x, I want to multiply it by function h. And I believe that was 3 halves x, what was it? 3 halves x minus 2. Okay, there we go. And now I want to subtract f of x. And this is where you're going to decide, what's best for you personally. Some people are going to go ahead and write the expression in parentheses so they remember to distribute. Some people are going to feel confident enough just to go ahead and distribute as you write it out. What would you prefer me to do? Just write it out? Okay. So f of x, if I remember correctly, it was negative x squared plus 3x minus 5. So I'm wanting to subtract this trinomial. So that means when I do start to subtract, I should get plus x squared minus 3x plus 5. Would everybody agree? Okay. All right. And once again, it just comes right down to your algebra skills, just what you've been doing for years. Somebody distribute that negative 6x for me. What do I get? Okay, so negative 9x squared plus 12x. And then we have the plus x squared minus 3x plus 5. Okay. And then just combine your like terms. We have how many x squareds? Okay, negative 8. Those are going to cancel. X's. Plus 9x. And then it looks like we have the plus 5 at the end. All right. Anybody having a hard time? Questions? Easy? Okay. Like I said, just the algebra. Okay, moving on. F. But what does F want me to do? It simply wants me to multiply the two. So function F was negative x squared plus 3x minus 5. Function G, 1 minus 2x, is that right? Okay. Unfortunately, I've forgotten how to multiply a binomial and a trinomial, so I need somebody to help me out. Okay. Kaushal, you were the last person to come up. Who would you like to see multiply this? Okay. All right. Philip, the choice has been made. All right. There you go, sir. All right. Okay, so we simply distribute each term. So negative x squared plus 2x. Oh. One little item. You're right about the plus 2x, but it is x squared times x. There we go, x cubed. There we go. Plus 3x. Minus 6x. There we go. Okay. And now plus 10. There we go. Okay. Now we just need to combine our like terms. Okay, so we have 2x cubed. Okay. Oh, and he is correct. I think that last 5 right there should just be a 5 and not 5x. There we go. Okay, so that actually changes it to how many x's? 13x. There we go.
Minus 5.
There you go. We can't go any further. That is it. Perfect. Okay. Questions? Okay. All right, let's take a look at the next one. Onward and upward. For what value or values of x is f of x equal to g of x? Okay, so this one, you're not performing an operation or even a composition with the functions. You're just setting up an equation. Graphically, you'd be looking for the intersection of the quadratic and the linear. But we're going to go ahead and do this by hand. So f of x, negative x squared, plus 3x minus 5, equals g of x, 1 minus 2x. Okay. All right, now we can go ahead and move any terms you like. Sandra, do you want me to move all the terms from the left to the right, or all the terms from the right to the left? Right to left. Okay. So I'm going to keep the negative x squared right here. Now, if I go ahead and subtract, or excuse me, add the 2x, what do I get? Plus 5x. Then if I subtract the 1, negative 6, and it equals 0. so as we've seen many times before in here already, we got ourselves a quadratic. Okay, probably the fastest, most efficient method is factoring. Okay. Now there are other methods, quadratic formula, completing the square. In fact, first period today, they solved it by completing the square. What would you folks like to do? Jake? Just factor it? Okay. Now, personally, if I'm going to go ahead and factor, I like my leading coefficient to be positive. So I just like to go ahead and multiply through in this case. That's just something I like to do. So x squared minus 5x plus 6 is equal to 0. Now, this is a different quadratic. If you looked at it graphically, it's going to have a different vertex, but the roots will be the same. And that's what we're looking for. We're finding the values of x that make this true. In fact, what are my two factors here? X, what? Not minus 6. It would have to be minus 3 and then minus 2. There we go. Okay. No. Okay. Now, how does that help me find my answers? There you go. Yeah, just set them equal to 0, and we'll know exactly what we're looking for. So x minus 3 is equal to 0. X would equal 3. If x minus 2 equals 0, x equals 2. Again, just good old algebra. Okay, nothing new here. Any questions? Okay. Everybody's doing well? Okay. We're functioning well in this lesson? You'll laugh later. That's what I like to tell myself. I'll just always say, you'll laugh later. Well, it makes me feel better. Next up, that was funny. Okay. J. Find an equation for g plus p of x. So what am I doing with the linear and the rational here? Just adding them up. Okay. Now, because it's a rational, that probably means I'm going to have to find a common denominator. Okay, so function g was 1 minus 2x, and I'm going to add that to p. I'm trying to remember off the top of my head, was it x plus 2 over x minus 3? Okay, thank you, Connor. All right. So now I need somebody to come on up and help me with this one. So let's keep that train going. Philip, who would you like to see come up and join these expressions? Anybody? Well, except for Phil or Kaushal. Kaushal just went up there. Kate is coming up. There you go, man. And I should say, I don't see a whole lot of volunteers, but everybody who gets chosen, they just have this enormous smile on their face as they're walking up to the board. See that everybody agrees with me. Okay. All right. So 1 minus 2x, x minus 3. Oh, you actually, that's okay. There we go. We don't need, all right. Okay, so we're going to multiply by a version of 1. Let's see. X minus 2x squared, and then we have minus 3 plus 6x. Okay. Okay, so now she's got an equivalent fraction for the first expression. So negative 2x squared plus 8x minus 1 over x minus 3. And there you go. And this is a perfect example. It's only after you get everything into one fraction that you've multiplied the numerators, you've combined your like terms, then as a last step, always ask yourself, can it be simplified by factoring? Okay, this would be a good problem to look at that. But that numerator, it is not going to factor. Okay, so that would be my answer. Okay. Negative 2x squared plus 8x minus 1 over x minus 3. Okay, questions? Okay. Okay, well, let's go ahead and look at our next section here. Okay, so I want to go back to finding a composite equation, but then I want to have a discussion about finding the domain of that, because these are going to be kind of unique. Find the composition, f composed with g, given f is the square root of x minus 1, and g is x minus 1 squared. Okay, so what I'm wanting to do here is find f of g of x. Okay, so how will I perform the substitution? The way I've written it, will I go ahead and plug function f into function g or g into f? G into f. You always start with that innermost function. So this is going to be f of the x minus 1 squared. Okay. So square root of x minus 1 would be square root of x minus 1 squared. See, there's the x, and then you have the minus 1. I plug g directly into function f. Is everybody okay with that? Now, where should I go from here? Or maybe a better question, can I simplify? Can I go ahead and just remove that radical? Okay, so I heard a yes, I heard a no. There are more no's than yeses. Okay. Now here, unfortunately, you can't do that. If there was no minus 1, then I could absolutely go ahead and take the square root of that. But when your radicand is broken up, and when it's a binomial or a trinomial, basically when it's terms separated by addition and subtraction, those won't allow you to actually apply the radical. And this brings up a big misconception, that a lot of people have in mathematics. If you see something like this, the square root of a squared plus b squared, a lot of people want to say it's a plus b. And it's one of those expressions, when you look at it, it would seem to make sense, but it's not true. If you take values of a and b and plug it in, they're not going to be the same. Okay? So if we can't just get rid of the radical, the best next step here would be just to expand and see what like terms I have. What is x minus 1 in squared? Okay, so that's x squared minus 2x plus 1. Now that right there, that is just x minus 1 expanded. Okay, so don't forget we have the minus 1 right here. So it looks like I've got what? X squared minus 2x. Okay, so x squared minus 2x. Okay, so I want to go ahead and show you. See, here's the thing that I was talking about. The one rule that I keep saying over and over again is that the outputs, okay, all the outputs for the inside function must belong to the domain of the outside function. Okay, well, this right here, what's the range of g of x? If I were to take a look at that graph right there, the x minus 1 squared. Okay. Okay. Well, let's go ahead and just sketch it. It's definitely the parent. What kind of shift is this? Is it horizontal or is it vertical? Horizontal. What direction? Okay, to the right. Okay. So x minus 1 squared. So it's 1 to the right. It's going to look something like this. Okay. Now, the range is okay. Are there any values of x that would cause a problem here? Because remember, we're substituting him into a radical function. Are there any values that we can't take the square root of? Well, I mean, we can take the square root of 2. It's going to be irrational, but it still exists. What kind of numbers am I referring to? Negative. So that's definitely going to play into the domain of this composite equation right here. In fact, let's go ahead and analyze this. We ended up with a radicand of x squared minus 2x. Okay, let's go ahead and sketch it. How much time do we have? Well, we got enough time to at least get started. Let's go ahead and first find his vertex. Probably not really necessary, but I think it's a good idea to spiral it back in. Does anybody remember what's that little expression involving a and b that would give me the x value of my vertex? Negative b over 2a. All right, so x equals the opposite of b over 2a. Well, the opposite of b, now remember, all we're doing right now is just focusing on the radicand. We'll get back to the radical in just a second. I'm just looking at x squared minus 2x. So the opposite of b would be a positive 2 divided by 2 times a. Well, that's 2 times 1, 2. Okay, so that's going to be 1. Okay. Well, how do I find the y value that corresponds to it? Plug it back in. So x squared would be 1 squared minus 2 times 1. What would that give me? Negative 1. Okay. So my vertex is at 1, negative 1. Definitely opens up. Can anybody tell me where he's crossing the x-axis? Where would x squared minus 2x cross the x-axis? Okay, Philip? 1, 0. Okay. Well, not 1, 0. 2 0 is going to be one of them, and there's another root. 0, 0. It's going to cross at 0, and it's going to cross at 2, just like you said. So x squared minus 2x is going to look something like that. Is everybody okay where we got the 0 and the 2? Or do I need to elaborate? Okay. Now, this is what we're going to contain within the square root. So let's kind of go back to what we just said. We can't take the square root of what? Any negatives. I mean, we know they're going to go imaginary, so we're only looking for values of x that are going to give me positive values. So this also connects to our inequality lesson. Okay. I'm looking for the places on this graph where it's considered positive. What am I referring to? Where it's above the x-axis. So I want this one right here, and I want this one right here. Okay. This is where x squared minus 2x ends up in a positive result. Okay. So what about this one here? Let me go ahead and highlight it in, let's say, green. What does that represent? That represents below, so that's a negative, right? So knowing this, can anybody now tell me what the domain of this composite function has to be? What are the only acceptable x? Copy. Okay, so say again, sir? Negative infinity to what? To 0. Now, would the 0 be included or no? Okay, so the square root of 0 is 0, right? So it's okay. Union to infinity, and that one bracket, the same reason we can include the 0. Okay. Because let's say, for example, if I choose any value of x between the two, like for example 1, we already saw what happens when x is 1. What kind of y value did we get? We got a negative value. If we take the square root of that, it's going to end up being imaginary. Is everybody okay what I did here? Okay, my analysis using the radicand? Okay, we'll try another example tomorrow. Okay, we'll try another one tomorrow, and we'll see what you think. Yes. Okay. Because what I'm trying to show you is that the domain of the composite function will be affected by the original functions you use. Okay. All right.